Hello and welcome. This is going to be an exploration into the modeling of the United States Census. In this video, it's going to be presented by myself, Matthew Kelly, my colleagues Matthew Komosinski, Bryan Jaager Ramirez, and Richard Wang. So this exploration is going to be derived from and inspired from the SIMIODE article, Population Modeling with the Census Data by Jean-Marie Linhart, a professor of mathematics at the Central Washington University. So what is the United States Census? Well, the United States Census is an instrumental part of the United States democracy, and it impacts all Americans. In the Constitution, it requires the census to be taken every 10 years, and it was the reason for the establishment of the United States Census Bureau. Every decennial, the U.S. Census Bureau is tasked with counting every resident in the United States, which can be a difficult task considering its population of over 330 million. So how'd they do it? Well, in the past, census forms were mailed to the households to be filled, but obviously not everyone would feel obligated to respond to these. So field agents were often sent to underreported areas to conduct a more accurate data pool. However, in the most recent 2020 census, the Bureau allowed residents to submit their census via phone, mail, or the internet, which resulted in higher participation rates. Why is it important? Well, there are a few reasons. For one, it's an instrumental factor in how both federal and state budgets are spent in which parts of the country. These budgets often affect infrastructure, schools, hospitals, and other government-supported programs. Another major reason why it's so important is because it also decides the House of Representatives seats. A quick reminder, the House of Representatives is the lower congressional house in Congress, and its representatives are based on the congressional districts allocated to each state based on the population recorded on the census. For example, after the 2020 census, Texas population grew and gained 2 seats, while New York's population declined slightly and lost a seat. As we can see, knowing the population changes in the country is an essential part of a functioning government. So how are we going to model this population change? Well, we're going to explore 3 different types: exponential, logistic, and Gompertz. The first one is the exponential growth. And this is the one that most people are most likely familiar with, and it's demonstrated in the top right graph. As we can see in the top left equation, it is dependent on the rate of change, denoted by R, and the population, denoted by P. Now we can actually solve this using methods and differential equations to get the function P of T, which will give us P naught is equal to the exponent of RT, where P naught is means the initial population and T it means the time. Now, not everyone watching this may be familiar with how we may solve this differential equation, so I'll give a brief run through of how we approach this. We know that this equation on the top right is a separable equation, so by separating each of the constants by their variable that impacts them, we can put the variable P on the left side and the growth rate R on the right side. When we take the integral of these 2 sides, we get the natural log of P is equal to the rate times T plus C. And if we're familiar with earlier algebra, we know that we can get rid of that natural log of P by taking the exponent of each side of the equation, which will then give us in the bottom right the P of T equation, which was previously stated. Our next model, logistic model, is also very similar to the exponential model, but it has a slightly different variables. So as we see in the top right graph, it initially acts very similarly to the exponential model, but as it reaches that carrying capacity, denoted by the red dashed line, the population rate tapers off until it reaches a horizontal asymptote where it will never cross that carrying capacity. In the top left, in the first equation, we can see that this logistic model can be represented mathematically with the change in P over T is equal to the growth rate times 1 minus the population over the carrying capacity times the population. Now, something important to note here is that this relationship, unlike the exponential, is dependent on multiple variables, including the growth rate, the population, as well as the carrying capacity. Now solving this differential equation, we get the bottom left equation for P of T. Now moving on to the next slide, this initially looks pretty complicated and pretty in-depth, and it is, but it follows the same essential steps that we explored with the first exponential model. We know it's a separable equation, we separate the variables, we then take the integral, and then once when we do that, we can get equation P of T. Now that equation x, which is denoted on the right, is the equation t that has a arbitrary constant c. Now, in our scenario, we can define an initial condition, P naught is equal to P of 0, shown in the bottom left, and that allows us to solve for C, which we can then plug back into the equation X to get our final P of T equation, which is the carrying capacity over 1 plus the carrying capacity times the initial population over the initial population times the exponent to the negative growth rate times time. Now, our final model we're going to explore is the Gompertz model, which is the change in population over time, just like the other ones. It follows a very similar path as the logistic model, although it has a slightly different variation. Once again, this is dependent on the carrying capacity L as well as the growth rate and population, and the equation P of T can be solved using differential equations to get the carrying capacity times e to the negative log over the carrying capacity over the initial condition times the exponent to the negative growth rate times time. For the sake of this video and for the sake of time, I will not go into depth on how this is calculated, although it does follow similar steps to the previous ones. And now I'm going to hand it off to my colleague, Richard Wang.
So now we get into per unit population growth rate, or Ppgr. So the Ppgr measures how much one person contributes to the growth in population over time. And we can see this equation on the right. So when analyzing the Ppgr for each of our three models, we end up with these equations on the left. From these equations, like Matt mentioned before, we can observe that unlike the exponential model, the logistic and Gompertz models take into account the population and the carrying or limiting capacity in their per unit population growth rates. If we assume that our limiting capacity L is greater than the population P, then when the population is small, the per unit population growth rate is higher than when the populations are large. If we think about this, it makes sense because the growth rate, or the rate of growth as a population reaches the limiting capacity should slow down and level off. Now, looking at the shapes of each population model curve from figure 3, we can see that the curves follow our line of thought. For smaller values of population, the growth and the slope of the curve increase over time, and as time goes on and population increases further, the slope of the curve decreases as population approaches the limiting capacity. Now, obviously, the exponential model does not take into account variables such as changing population and limiting capacity, and as such, grows only based on the constant growth rate r. This is why we can observe the exponential model growing to infinity. Thus, we can immediately rule out the exponential model as a viable model for population, as it ignores many of the natural limitations we experience.
So in this part of the video, we're going to be comparing both the Gompertz model and the logistic model. And on the left side of the presentation, you can see what each variable represents. We have L, which is the limiting capacity, also commonly known as the carrying capacity, depending on what your teachers call it. P represents the population. R, in this situation, is a constant. P of O is the initial population, and T is time, which, as you can see from the bullet, we represent that in years for this presentation. Before we get into the actual graphs, the equations we use, which you will see on the next few slides, are at the bottom right of this slide here. It's the P of T for both Gompertz and logistic model. So to start us off, we have the logistic model graphs. On the left graph you can see here is when the P of O, which is the initial population, is 1. And at the bottom of the graph, you can see the equation that we use to plug in. And the 0.1, you might be wondering, at the top is the R in this situation. And on the right graph, you can see the P of O is 90, which is closer to the L carrying capacity, which you can see at the bottom is 100 for both graphs. And this makes sense when we look back at what Richard said, because in a situation on the left side, the initial population is further away from the carrying capacity, which means it will take longer for it to slow down and level off, whereas the P of O in 90 is a lot closer to 100, so it would be a lot faster to slow down and level off. And looking at the Gompertz model graphs, it's the same idea the graphs are just slightly different due to the equations being different, as you can see from the bottom of the screen. But we kept the variables the same. The P of O on the left is 1, the P of O on the right is 90, the L is for both graphs is 100, and the R we have at 0.1.
So now that we have our equations that can kind of simulate the population growth, we want to analyze how these equations are reflective of the actual data. And the way we're going to do this is by using the nonlinear least squares parameter estimation. Now this derives from the linear least squares parameter estimation, which I'm sure most of us are familiar with. A quick recap, a major part of this is something called residuals, which is in simplest terms is the error in result, or where the y values denoted by the black dots, what their distance from the function, the blue line, and yeah, so it's just their distance from the function. Now, the ordinary least squares is a way to take the best line that minimizes the residuals, and this can also be referred to as the line of best fit, and it's essential in creating predictions that are accurate, that take into account variations in the data. Now, we're not dealing with linear estimations with our growth models. So in order to be able to still make accurate predictions and estimations with our variables, we're going to have to take the linear relationship of the function to get good initial parameters and our line of best fit. Now, the way we're going to look into is the exponential and the logistics. And you might be asked, how are we going to linearize the exponential and logistic equations? Well, knowing that they are functions that are derived from the exponent to a constant, we can take the log of each equation, and that will give us a linear relationship that can further be analyzed with their residuals.
All right, so the coefficient of determination. This basically is a value that tells us how linear a model is and how it compares to a linear model. This is represented by r squared and is found in the equation as follows: 1 minus the sum of a residual squared over the sum of another residual squared, or it can be found using 1 minus SS res over SS tot. An example of the coefficient of determination is as follows. I have a graph that is a bunch of random values and a line of best fit on the graph, and the equation for the line of best fit is found in the top right, as well as the coefficient of determination. So how do you find the coefficient of determination? I have the equation on the right, and I expanded it a little bit to try to make it easier to understand. So to find SS res, you take your y value minus the y value on the line of best fit, which can be found plugging your x value into the line of best fit equation. And so you would square that, and then you would do that for every single point, and you would add them all up. And that is your SS res. Your SS tot is very similar. You take your y value minus, instead of the line of best fit, you would minus the y bar, which in this case is the 1.02, which is the average of all your y values. So you do that, then you square it, and then you have to do that for all of your points, add it all up, and that's your SS tot. So then you would just plug your SS res and SS tot into the equation, 1 minus SS res over SS tot, and that gives your coefficient of determination. In this case, as you can see in the top right, it equals 0.0957. This is not a very linear model. In general, the closer r squared is to 1, the better fit it is to a linear model. You could also think of this as a percent. If you times r squared by 100, you get 9.57% or 9.57% linear. So another coefficient of determination is the adjusted coefficient of determination, which is basically the same as r squared, except when it takes the number of variables and data points into account. This, instead of being just represented by r squared, it is represented by r squared bar. So this is a different equation than the one I previously mentioned, and it has different variables. So the variables are n equals number of data points, so all of your x and y's, P is the number of parameters or variables, and R squared is coefficient of determination, which I mentioned previously. And so R squared bar equals 1 minus parentheses 1 minus R squared close parentheses times n minus 1 over n minus P minus 1. So how does this relate to what we've been saying? Well, basically, it makes it easier to compare how linear a model is to how linear a different model is. So you could basically just compare different models this way. And so a kind of a rule of thumb when it comes to should I use the adjusted coefficient of determination or just the regular coefficient of determination is if the number of variables are very similar between the models, you should use the regular coefficient of determination. And if they're varying a lot, then you should use the adjusted one. In this case, these models have very similar parameters and variables, so you would use the regular R squared.
As my colleague just stated, we are exploring the R squared values related to each of the three models. Here you can see the sample data that was utilized for these calculations. Seen in the bottom left, the exponential method was used with the equation 1 over P times R times P. The R squared value is 0.8462. While that is good, the Ppgr should be going in a negative trend since the Ppgr should decrease while the population increases over time. In the top right, you can see the Gompertz method model. It is shown using the equation 1 over P times R times log of 1 over P times P. Here, the R squared value is a little lower, but it's still good at 0.7866, and it has a good trend down. But when comparing it to the logistic model, found with 1 over P times R times 1 minus P over L times P, it has a better linear negative trend with a perfect R squared value of 1. Predictions can be made from this logistic method graph because of its linearity. The best fit line allows for a prediction of the Ppgr when a certain population is hit. Though predictions aren't always accurate, the error for this could be found very easily with the equation shown. Predicted minus actual divided by actual to determine if the model is still good after time.
So after everything we have learned today, and after all these great ways of learning about the census, you might be asking yourself, what is the best equation to properly represent the census? And the answer I have for you today might not be surprising, and that answer is the logistic equation we believe is the best way to go. And we believe this way is the best because after seeing all those graphs, it gives the best relative accurate data for the census compared to the Gompertz, and definitely compared to the exponential. But that's not to say that Gompertz and exponential will not work in other censuses. That's a tongue twister for you. But we believe in this particular situation, logistical equation works best. We appreciate you taking the time to watch our video today. If you enjoyed the video, leave a like, subscribe. If you dislike the video, leave a dislike. Comment below any tips, any questions you have. We'll try our best to answer them. And on the next slide here, you will see the sources that we use for this video. Once again, thank you for watching. Stay safe out there, and until next time.